Welcome, future A student. You have made an incredible choice today because in the next few minutes, we are completely conquering chemical bonding, ionic, covalent, metallic, and everything in between. Chemical bonding is the foundation of chemistry. Understand it, and you can explain why salt dissolves in water, why metal conducts electricity, why diamond is harder than steel, and why water is bent shaped. And in JAMB, bonding questions appear every single year. In these few minutes, we are going to do a total coverage, maximum marks. Your A grade starts right here. Let's go. Why do atoms form chemical bonds? The answer is the octet rule, one of the most powerful principles in all chemistry. Atoms are more stable when they have a full outer shell of electrons, just like noble gases. Noble gases, helium with 2, neon with 8, argon with 8, all have full outer shell. That's valence shell, and are incredibly stable and non-reactive. Every other atom wants to achieve that same stability. There are 3 ways atoms achieve this: ionic bonding, metal transfer electrons to non-metals. What about covalent bonding? Non-metals share electrons with other non-metals, and metallic bonding, metal share electron in a sea that flows between them. These 3 bonding mechanisms explain essentially all of chemistry, and the noble gas target is always the nearest noble gas. Sodium targets neon, chlorine targets argon, calcium targets argon. This concept is the master key to chemical bonding. Let's build ionic bonding from scratch, and I want you to watch this carefully because this is exactly what JAMB asks. Sodium has the configuration 281. It has one lonely electron in the outer shell. It desperately wants to lose that electron to become 28 like neon. Chlorine has configuration 287. It has 7 electrons in the outer shell, needs just one more electron to complete the octet to 288 like argon. So what happened? Sodium gives its one outer electron to chlorine. Sodium becomes Na plus, a positive ion called a cation. Chlorine becomes Cl minus, a negative ion called an anion. Now here is the magic. Opposite charges attract. Na plus and Cl minus are pulled powerfully together by electrostatic attraction. That attraction is the ionic bond. The resulting compound is sodium chloride, table salt. Look at the table on the screen. Magnesium loses 2 electrons to become Mg2 plus. Oxygen gains 2 electrons to become O2 minus. Calcium loses 2 to become Ca2 plus. This electron transfer pattern is the essence of all ionic bonding. Ionic compounds all share characteristic properties that flow directly from their structure. They form giant ionic lattice, millions of positive and negative ions arranged in a regular 3D pattern, held together by strong electrostatic forces in all directions. Because these forces are so strong, ionic compounds have high melting points. Sodium chloride melts at 801 degrees Celsius. Magnesium oxide melts at a staggering 2852. What about electrical conductivity? This is a favorite JAMB question. Note that in solid state, ionic compounds do not conduct electricity. Why? Because the ions are locked in fixed positions in the lattice. They cannot move to carry charge. But when you melt the ionic compound or dissolve it in water, the ions become free to move and electricity flows. This is exactly how electrolysis works. Remember, it's free moving ions that carry current in ionic compounds, not electrons. Solubility. Ionic compounds generally dissolve well in water because water is a polar solvent that can interact with and surround the charges of iron. And the strength comparison is that magnesium oxide has a much higher melting point than sodium chloride because Mg2 plus and O2 minus carry double charges, creating 4 times the electrostatic force compared to +1 -1 of sodium and chloride. Covalent bonding, the most common type of bonding in the entire universe. When 2 non-metal atoms meet, neither wants to give electrons to the other. They are both electron hungry, so they do something brilliant. They share. A covalent bond is a shared pair of electrons with each atom contributing 1 electron to the pair. Both atoms will then count the shared electrons as their own, and both achieve full outer shells. The simplest example is hydrogen. Each hydrogen atom has 1 electron and need 1 more to complete its inner shell of 2, like helium. So 2 hydrogen atoms come together to share their electrons. That's H. As you see on the screen, now each hydrogen sees 2 electrons, a full shell. The bond is represented as H to H. In chlorine gas Cl2, each chlorine atom has 7 valence electrons and needs 1 more electron. Each contributes 1 electron to a shared pair to have Cc. As you see on the screen, each chlorine now counts 8 electrons, a full octet. Here is your prediction formula for how many bonds an atom will form. Subtract the atom's valence electrons from 8, then divide by 2. Oxygen needs 2 bonds, nitrogen needs 3 bonds, carbon needs 4 bonds, which is why carbon chemistry is so rich and complex. Carbon can form chains, rings, double bonds, triple bonds, all because it makes 4 bonds. Covalent bond comes in 3 flavors, and JAMB tests all of them. A single bond shares 1 pair of electrons, that is 2 electrons shared, written as a single line, HH. A double bond shares 2 pairs, that's 4 electrons shared, written as double line in oxygen or carbon. A triple bond shares 3 pairs, 6 electrons shared, written as a triple line like in nitrogen to nitrogen. So now here is the critical relationship to memorize. The more pair of electrons shared, the shorter and stronger the bond. Single bonds are the longest and weakest. Triple bonds are the shortest and most powerful. Nitrogen gas has a triple bond. Nitrogen triple bond nitrogen with a bond energy of 945 kilojoule per mole. This is one of the strongest bonds in chemistry, which is why atmospheric nitrogen gas is so incredibly unreactive. Even though nitrogen makes up like 70% of our air, it sits there doing almost nothing because breaking that triple bond requires enormous energy. For JAMB questions, CO2 has 2 double bonds of oxygen, double bond carbon, double bond oxygen, linear at 180 degrees. Water has 2 single bonds of hydrogen to oxygen to hydrogen, bent shape at 104.5 degrees. This shape comes directly from the bonding. Not all covalent bonds are created equally. When 2 atoms with same or very similar electronegative share electrons, they share them equally. We call this a non-polar covalent bond, like in hydrogen, CSCl, O2, nitrogen, N2. In all these cases, both atoms are identical, so there is 0 pull to either side. The electrons sit perfectly in the middle. But when atoms of different electronegativities share electrons, like hydrogen and chlorine, the more electronegative atom pulls the shared electrons closer to itself. Chlorine is more electronegative than hydrogen, so electron pair spends more time near the chlorine end. This creates a polar covalent bond, a small negative charge on the chlorine side and a small positive charge on the hydrogen side. We show this with delta minus on chlorine and delta plus on hydrogen. Electronegativity fact. Key fact is that fluorine is the most electronegative element in the entire periodic table at 4.0 on the Pauling scale. Then oxygen at 3.5, nitrogen and chlorine tied at 3.0. JAMB asks which element is the most electronegative. Almost every single year, the answer is always fluorine. And delta En boundary for bond type less than 0.4 is non-polar covalent. 0.4 to 1.7 is polar covalent, and 1.7 is ionic. Metallic bonding, the third and final bonding type, and it explains all the properties that make metal so incredibly useful in a metal Each atom releases its valence electron into a shared sea of delocalized electrons that flows freely throughout the entire structure. The remaining positive metal ions sit in a regular lattice held together by their attraction to this sea of electrons. The sea of electrons is the key to everything. Why do metal conduct electricity? Because those delocalized electrons are free to move. Apply a voltage and electrons flow in one direction, carrying charge, creating an electric current. Metals conduct electricity even though in the solid state, no need to melt them unlike ionic compounds. Why are metals malleable? Why can you hammer gold into thin sheets? Because when you hit a metal, the layers of positive ions slide over each other and the sea of electrons simply flows to fill the new position. The metallic bond doesn't break, it just reorganizes. Try that with an ionic compound, you will crack it because same charges, ions end up next to each other and repel. Bond strength is that more valence electrons means more electrons in the sea means stronger bonding. Sodium has one valence electron and met at 98 degrees. Magnesium has two and met at 650. Aluminum has three and met at 660. Iron with more electrons met at enormous 1538 degrees Celsius. There is a fourth type of covalent bond that JAMB tests, the coordinate or dative covalent bond. It sounds complicated, but the concept is simple. In a regular covalent bond, each atom contributes one electron to the shared pair. In a dative covalent bond, one atom, the donor, provides both electrons of the bond. The other atoms, the acceptor, must have an empty orbital to receive them. Classic example is nitrogen in ammonia. Na3 has a lone pair of electrons, two electrons not involved in bonding. When ammonia gets a hydrogen ion plus, that's H plus, which has a completely empty 1s orbital, nitrogen donates that lone pair to the hydrogen plus. A bond formed, and now we have ammonium ion plus. That's once formed, all four nitrogen hydrogen bond in ammonium are completely identical. There is no way to tell which one was a dative bond. Another example is water plus hydrogen plus gives hydronium ion H3O plus. Oxygen donates its lone pair. Boron trifluoride accepts a lone pair from ammonia because boron has only 6 electrons and empty orbital. Remember the arrow in structural formula for dative bond points from the lone pair donor to the acceptor. The shortcut is that lone pair plus empty orbital equals dative bond. Now we put it all together, the master comparison table that connects bond type to physical properties. This is the slide that gets you those identify the bond type marks in JAMB. Ionic compounds high melting point conducts when molten or dissolved in water, soluble in polar solvents. Simple covalent bond, low melting point because you only need to overcome weak forces between molecules, not break the covalent bonds themselves. Conductivity, soluble in various solvents. Giant covalent structure, very high melting points, even higher than ionic because you must break actual covalent bonds to melt them. Diamond, for example, melt at 3550 degrees Celsius, higher than almost anything else on Earth. No conductivity, out of metallic bonding. High melting points, excellent conductivity in solid state, unlike any other bond type. One crucial exception to memorize: graphite is a giant covalent structure, but it conducts electricity. Note that each carbon in graphite forms only 3 bonds, leaving one delocalized electron per carbon that can move freely between the flat layers, making graphite a good conductivity. This is why graphite is used as electrodes in electrolysis. JAMB exam strategy is this: given a list of properties, identify the bond type by checking conductivity first. That eliminates most options immediately. Now pause, it's JAMB practice time. Read the clue carefully. Melting point to 2852 degrees Celsius. Conduct electricity when molten, but not when solid. Soluble in water. What type of bonding? Answer in the comment section. The answer is B, ionic bonding, and the compound is magnesium oxide, MgO. Let me explain each clue. Melting point 2852 degrees. This is very high, consistent with strong ionic lattice. MgO is even harder to melt than NaCl because Mg2 plus and O2 minus carry double charges. Conduct only when molten. This is defining signature of ionic compounds. Ions are locked in the solid lattice and cannot move. Melt it and they become free. Current flows. This immediately rules out metallic, which conducts in solid state, and covalent, which generally doesn't conduct at all. Soluble in water, consistent with ionic, and giant covalent is ruled out because it has no conductivity even when molten. No free ions, and is generally insoluble. Perfect reasoning. JAMB often gives 3 clues. You only need one of them to identify ionic bonding. But using all 3 to cross-check is exam strategy at its best. Now to the second JAMB question they are treating here, and this is about ionic bond formation with electronic configurations. Calcium has atomic number 20. Write its configuration 2882. Oxygen has atomic number 8, configuration 2826. Now, calcium has 2 valence electrons and wants to reach argon's configuration of 288. It will lose 2 electrons to Ca2 plus to become calcium ion, that's Ca2 plus, configuration 288. Oxygen has 6 valence electrons and wants to reach neon configuration of 28. It needs to gain 2 electrons to become O2 minus, configuration 28. Answer in the comment section. What will be the answer? And the answer is C, because calcium ion with configuration 288 and oxygen ion with configuration 28, the formula is CaO. Charges of +2 and -2 cancel each other in a 1-to-1 ratio. Let me explain the wrong options. If you pick option A, it is wrong because calcium has 2 valence electrons, not 1. It cannot form Ca+. It will end up as 289 if you pick Ca+, which makes no chemical sense. Option D is wrong too because Ca2+ loses its outer shell entirely. The correct configuration after losing 2 electrons from 2882 is 288, not 2882. This is a very common JAMB trap. Writing the ion configuration incorrectly, but by not removing the outer shell, write the original configuration, count the electron lost or gained, remove them and write what remains. And here it is, your complete chemical bonding sheet: ionic, covalent, giant covalent, metallic and dative. All 5 bond types, their formations, melting points, conductivity patterns, the electronegativity boundary rule. Below 0.4 is non-polar covalent. 0.4 to 1.7 is polar covalent. Above 1.7 is ionic. Fluorine is 4.0, most electronegative. 3 golden rules that govern all bonding is that rule 1, metal lose electron and form positive ions. Rule 2 is that no metal gains electron and form negative ions. Rule 3 is that every atom aims for the noble gas configuration. These 3 rules can solve any JAMB bonding question you encounter. Screenshot this right now. Print it, post it where you study, share it with every chemistry student in your class, even your WhatsApp group. This cheat sheet is worth exam mark. You absolutely legend. In these few minutes, you just mastered all chemical bonding, ionic electron transfer, covalent electron sharing, metallic sea of electrons, polar and non-polar covalent, dative bonds, property comparison. You have covered everything JAMB has tested in this topic for the past years in one compact session. Here is the truth about bonding. Once you understand why atoms bond, the octet rule, the drive for stability, every other concept in chemistry becomes clearer. Redox becomes clearer, electrolysis, acid-base chemistry, organic chemistry, they all connect back to bonding. You have just unlocked the master key. Now, please do these three things right now. Like this video, one tap massive impact, subscribe, and ring the bell for your next JAMB Blitz, and share this with every chemistry student you know. Let's get the whole class scoring A. Comment below which bond type you found hardest. Is it ionic, covalent, or metallic? And stay tuned, because next up is VSEPR, theory and molecular shapes. In few minutes, we will see you there. Keep going. Your JAMB grade A is coming. Muff cares.